All right, we're going to start with chapter 28, part 1, reflection and refraction. We're going to look at the law of reflection, plane mirrors, and curved mirrors for the first part. Okay, so let's look at this cool picture. All right, so here we have a gentleman, a physics teacher, flying, seemingly flying. Okay, so what is going on here? Well, um, since none of you are out there in the studio audience are going to answer, then let's take a look at this because it's done with mirrors. You may notice that this gentleman is basically balanced, it looks like, on a mirror. So here is a mirror that goes through his legs, so he's very brave to be balanced on this mirror, which looks like it could slice him in half now that you noticed it. Okay, but that's not actually what's happening. See, this is his right leg, but this is not his left leg. His left leg is behind the mirror. He's standing on his left leg behind the mirror where you can't see it. And so, what you're actually seeing there, this is the reflection of his right leg. So, he is not balanced, standing, or flying on the mirror. He is standing with one leg behind the mirror. Okay, so you're seeing the right leg and the reflection of the right leg. So this is how musicians do it with mirrors because our brains don't know about mirrors. We treat everything as real. Okay, so let's look at the reflection. So we've talked about how light will interact with atoms, and just as sound interacts with tuning forks, your book says. But the idea is yes, light will give energy to electrons, it interacts with them, and then it can be repelled or released as a reflection. Okay, now there's the principle of least time, which we aren't really going to cover, but go ahead and read about it. But the idea is that the path that light will take is the shortest place, the shortest time to go from A to B, where it actually has to hit the mirror. And the thing is that any path that you draw, the shortest one is the one where the angles are equal. So remember we talked about in sound how the angle of incidence and the angle of reflection were the same. And so that is, of course, how it turns out for light. So for light, the angle of incidence equals the angle of reflection. Now, when we're drawing a mirror, we draw a straight line if it's a flat mirror, but it has one side smooth and the other side has these little things on the back that look like little hairs or something, and that's supposed to be indicating the back side of the mirror. Okay, so you've got one smooth surface, the reflective surface, and then you've got this hairy side, which is the back side of the mirror, which is dark. Light doesn't get there. Okay, and remember we're measuring angles to the normal, the perpendicular line, right? So the angle is measured here, not to the mirror. So a perpendicular line, the normal you need to draw when you're thinking about angles. Okay, so which card will you see in the mirror? And so to do that, you need to think, okay, well, the light has to reach the eye from this point. So you need an equal angles thing. So it looks like card 2. That will give me equal angles. It's really badly drawn angle, but hopefully you get the idea. Okay, now let's look at why we see objects in a mirror. And why, if it's a flat mirror, we see an image that is the same size as the object. So it's the same size. And we see it, though, at a position behind the mirror where reflected rays converge. So let's talk about your giant eyeball before we totally look into this. So let's skip a bit. Here we go. Here's your giant eyeball. And we've talked a little bit about eyeballs before, but let's follow the path of light in the eyeball. So I'm going to take, whoops, this color, nice magenta. Okay, so representing the flower petals here. The idea is that white light comes in. Since it's a magenta flower, that means by selective reflection, it's reflecting light of only the magenta colors, which is red and blue. And so it's reflecting those in all directions. Some of those are going to enter the eye. So from this one point, there are many beams of light, and some of those enter the eye, and a lot of them miss. The ones that enter the eye are going to be bent by the lens, okay, so their path is going to change, and it's going to focus that light down to the back of the eyeball. So this light is going to get focused to the back of the eyeball. Now let's take some green light from a leaf. Okay, so again, sunlight is hitting this leaf and light is radiating in many directions. Some of those are going to hit the eyeball and go into the pupil. Now, when those hit, and in the lens is going to focus those. And the thing is that the point where those get focused is on the back of the eyeball. But if you'll notice, it's above where the flower petal was focused. And in fact, all the points of light that are radiating from each point here will get pasted onto the back of the eyeball, focus there, and the flower will get drawn out on the back of the eyeball. So you've got the flower back there. It's upside down though, and that turns out to be okay. For a spherical lens, objects will be upside down at their focal point. And so anyway, that's what's going on here. So we've got the object upside down, and your brain just learns to work with that. So when you're a baby and you're reaching out to touch things, one of the things you're learning is where that object really is. And so your brain learns that when the object is down below, you reach up, and when the object is up, you reach down below, and so on. It's your brain is learning where the image and the object connect. And so anyway, so that's one of the things why babies need to touch stuff. And in fact, your brain can be retrained. They did an experiment years ago where they strapped people into prism-like headsets that would reverse the image of the world, and people had to wear those for weeks, and their brains adapted. And after a while, they were okay with the world being upside down. And then they took the goggles away, and people readapted. They flipped back over their eyesight. So it's something that goes on in our brain, all right? It's not something hardwired into us. Anyway, so we learn to take light that is spreading out from a point, and our brain, and it's focused on the back of our eyes, and our brain figures out where that is by tracing back the beams of light, basically. All right, so what does that have to do with this picture? Okay, so the idea is that when your giant eyeball over here is collecting up these beams of light, then the way your eyeball knows where objects are is it follows these beams of light backwards. And so then your brain knows where the object is. The thing is, people don't, the brain doesn't know about mirrors. We aren't set up for the idea of mirrors, really. So for our brain, we just follow the light backwards. And then we think that the object is here. So our candle would be in this location, which is the image of the candle, but our brain thinks it's real. So there's a real object and an image that our brain has located. Anyway, so for a flat mirror, the distance of the object to the mirror is the same as the distance to the image in the mirror. And this kind of image is called a virtual image. A virtual image is one where the light never actually goes through that point, because the light never did. This light was reflected off the mirror. It never actually was back behind the mirror. So that's what makes it virtual. A real image has light that passes through it. Okay, so anyway, so a flat mirror or plane mirror gives you the image size is the same as the object, and the image distance is the same as the object. Okay, now when you look at a mirror, sometimes people say left and right is reversed, and that's not quite true. The only thing that's really reversed is the front and back axes. Okay, so what's going on? Well, when you look in a mirror, you get fooled because your brain is used to seeing real people. So let's say that you have one eye that's a little bigger than the other, and you've got a dimple on one side of your mouth, and you part your hair like this. Okay, when you look in the mirror, you see your image reflected back at you, and you think it's a real person. Okay, but you think it's a real person who has the opposite thing. So you think the dimple is over on this side, you think the big eyes over here and the small eyes there, and the hair is parted like this, because that's what you think the real person looks like. And so you're seeing it as another person. So you get their left and right because you're used to that, right? You look at a person and you say that's his right hand, even though it's on your left, right? Correct. So we're used to reversing images to because when we look people in their faces, we know which side is their left and which is their right. So we tend to do that when we look in a mirror too. But the mirror isn't reversing them, it's us. We're the ones who reverse them. So it used to be because people saw themselves in a mirror. When they saw a photograph, they didn't really like it. The photo showed them as other people see them. And that actually looks reversed left right for a lot of people. Nowadays we take so many selfies, it's not so much of a shock. But yeah, people used to have trouble with that reversal idea. Okay, now when you have a curved mirror, then what you have is a different size image. And so for a convex mirror or a concave mirror, now it's always easy to remember concave. So this would be the concave one because it's like a cave. This is the convex one. And so a convex mirror, the idea is that the mirror is bending outward, which means that the beams of light go up at a steeper angle, which makes a smaller image. And so it's still obeying the laws of reflection, equal angles, but because of the curvature of the mirror, then it bends the light away or towards more. So what happens with this is you end up with a virtual image, but it's smaller and it's closer to the mirror. So in other words, the image distance is smaller than the object distance. And for the concave mirror, what happens is its mirror is tilting towards you. And so what happens is the beams of light get tilted towards your eyes, and that pushes them outward like this so that you see it as a larger image. So in this case, the image distance is greater than the object distance. So larger and farther away. Okay, so let's look at this next picture. Remember these ideas. And here you can see this guy is reflected in this pan. Can you tell if the surface is concave or convex? Well, you can, because look at his head, it's smaller. So since it's smaller, this must be a convex surface on that pan. Now, metals are really good reflectors. They're very shiny because when light shines on a metal, then the electrons vibrate and the energy is reflected. So it's not being absorbed or scattered, it's being just reflected. And shiny things like this, that's called specular reflection, where the beams of light are hitting a smooth surface so they stay together. So you get a really good image. Okay, we'll talk later about diffuse reflection, where what happens is when the beams hit, they hit a rough surface and they go in various directions. Okay, so anyway, but metals have specular reflection. Okay, now parabolic reflectors are all around us. They're behind light bulbs, say, in your flashlight, or at least they used to be. They are your satellite dish. And the idea is that beams of light or radio waves coming from your satellite, okay, where you're getting your TV signal, what happens is that parallel beams of light in a parabolic reflector will be reflected to focus at a point where you would put your detector, right, your sensor, and your receiver, it's called. So anyway, but that's the idea. Parallel beams of light come in and they are gathered and they focus at one point. Okay, now Einstein invented the reflector telescope, because one of the problems with lenses is that for lenses, the light that is different colors can go in different directions, and that's called chromatic aberration. And so that makes images of objects far away, like stars, the colors, if it's a white star, it has lots of colors, and so it makes it all smeary. So anyway, so chromatic aberration meant that telescopes made out of lenses aren't always very, very good. So Newton invented one that just had a mirror. So there's a mirror down here at the bottom and an open tube at the top. And beams of light from stars far away come down into the open tube, and then they reflect off the mirror. And they will get focused to a point. There's a eye piece here, so the light comes out, so you just bend your head over and look in. But that's the idea, is that the light is focused by a mirror instead of a lens. And that makes it much better because there's no chromatic aberration. Now, we've got a pig here because I've got a demonstration to show you. All right, so let me turn on some lights, grab the old camera. All right, take the camera over, and we're going to look at this pig. Okay, so you see the piggy there. There he is, cute little pig, right? So if I try to touch him, here's a pencil. Can't touch the pig. Can't knock him off here. Now, why is that? Well, that's because the pig isn't really standing there. This little pig, even though I can go around and look at him from different directions. But the problem is we're having a good cameraman would help. Where is he? Well, it turns out he's actually down underneath. So there's an image of the pig on top, and the real pig is down there far below inside this dish. Okay, so when I open this up, This is actually two parabolic reflectors. And the pig is down below. But we see his image up above. Okay, so let's go explain that. Okay, so here we've got our piggy. And as you saw, he is inside some parabolic reflectors. So dishes shaped like parabolas. So there's one. And then there's a second one. The second one has a hole in the top. Okay, so what's happening with the light from the pig? All right, so what's happening is light from this pig is spreading out. Okay. And so what happens is that when it hits the parabolic reflector on the top, one of the cool things about parabolic reflectors is they will focus parallel beams of light. But that means that light that is spreading out from a point will turn into parallel beams of light. So they will be reflected and now be parallel beams of light. But now they hit the parabolic reflector on the bottom. And parabolic reflectors take parallel beams of light and they reflect them and focus them at a point. So these beams of light are now going to get focused up above. And so every point on the pig gets repeated up above until we end up with a pig drawn out by beams of light. And then that light goes into our giant eyeballs, right? And we see a pig. Now, this is a real image because the light is actually going through it. And so remember, virtual ones, the light never went through that point. But in this case, this little piggy here really did have light pass through it and cross and focus at that point. And that's why we think there's a pig in that location. Okay, so parabolic reflectors can be dangerous because they focus light. They're handy, but they also can be dangerous. So there was the Videra Hotel death ray in Las Vegas. An architect built a hotel with a curved surface, and having forgotten all his physics, he forgot that this parabolic surface would reflect and focus light. And that's what happens. Sunlight, parallel beams of sunlight from the sun, hit and focused down by the pool. So people's towels were burning and people were getting burned by this rays of light hitting down below. Something similar happened in England. They built a building for some reason with a parabolic front on it. And so light from the sun was coming in and getting focused across the street. Where some buildings there, the shops, were getting their carpet burned inside the buildings as it would focus. And it would, that people found they could cook on the sidewalk. So you can cook an egg on the sidewalk because of the death ray from the building. So anyway, what these buildings both did was have to replace windows or put coatings on windows so that they would not reflect light like that. Okay, so those are those. So a mirror usually is a specular reflection of some sort. A diffuse reflector is a rough surface. Most surfaces are rough, right? So they're diffuse reflectors. And so that helps us to be able to see the colors. We're not just seeing the light bulb, we're seeing the thing that we want to see. And so anyway, so rough surfaces are around us mostly. Now, they don't have to feel rough to a human, but to a beam of light, it seems rough. So what happens is parallel beams of light will scatter, and then we can see from any direction that certain color. Whereas in a mirror, you have to have your head just the right location to see something. Okay, so books are made to be a little bit rough, so that because you don't want it reflecting the sun or your lamp, you just want to be able to read the words. So you want it to be a diffuse reflector. If it's a glossy book or a glossy magazine, then what happens is that's harder to read because you have reflections from the light. Now, whether something is diffuse reflector or a specular reflector also depends on the size of the wavelength, as we were just talking about. So for radio waves, this is a polished or specular type reflector for radio waves because they're large. And so the radio waves get reflected off this dish and come up to the receiver. Even though this is a giant dish, as you can see, it's on top of a building here. But to make it light enough to be used, it's also an open web of metal that to our eyes looks like it's full of holes. But the radio waves are so much larger than the light waves we use for visible light that that to radio waves it looks like a polished surface. And so beams of radio waves are reflected back to this receiver. Anyway, this receiver, this radio antenna actually has a movie about it. If you've never watched it, it's very funny. It's called The Dish. And it's about this receiver, which was the one that picked up the Apollo moon landing, the first step on the moon. And it's a wonderful story. It's set in Australia, and it's very funny because Australians know how to have a good laugh. Anyway, so usually I give extra credit. There's a somewhere there's an extra credit opportunity with a paper you can fill out to show that you watched The Dish. So you might see if your parents have it on their shelf. It's not that old, but they might have it around. It's not on Netflix anymore. Okay, but anyway, really good movie. All right, so that's the end of part 1. So for part 2, we're going to go look at refraction and mirages. Okay, and